So if we're going to turn the Earth into an interstellar cab, can we at least swing by Pluto on the way out? I've always wanted to see Pluto up close and personal. Hi, I'm Mike Siegel. I'm an astrophysicist. I write for Ordinary Times, and this is The Throughput. So I've been promising you a big movie for a while, and this is it. I was alerted to the existence of this movie by a viewer who described it as Chinese Armageddon, and I thought they were being a bit glib, and then I watched it, and I thought that was a pretty accurate description. The movie is called The Wandering Earth, and it's about the Earth going on a voyage out of the solar system powered by these giant engines. And I thought at first this must be some obscure movie I'd never heard of, but it's actually was based on a short story by Liu Cixin, the author of The Three Body Problem, which won a Hugo Award a few years ago, and was one of the biggest successes in Chinese movie history, making $700 million, and was actually a big critical success. So the plot of The Wandering Earth goeth thusly. The sun is unexpectedly becoming a red giant 4 billion years early. And to protect the Earth from being scorched, the Earth government constructs these giant engines to push it out of orbit and direct it towards Alpha Centauri 4 light years away to be safe. As you can probably tell by the plot description, this is quite fantastical. So we'll be talking a lot about the science here. I may not have long video clips with this. I'm going to be watching it on my laptop here. But this is a Chinese movie being streamed through Netflix, so I have no idea what the copyright bots are going to do to me if I try to show clips from this. So if it comes to that, I'll put up stills and tell you what's happening so you can at least follow along.
The sun is rapidly degenerating and expanding. At this rate, the sun will engulf Earth in 100 years. Within 300 years, the solar system will no longer exist.
The idea that the sun is entering into its red giant phase early. It is true that the sun will one day become a red giant 4 billion years into the future. It's not going to do that in the next 100 years. That is literally impossible. Here's how we know. What causes the sun to become a red giant? What happens is that it's burning hydrogen in its core into helium, and eventually that inert helium accumulates in the core to form what we call helium ash. That helium ash is non-reactive. It's not hot enough for the helium to fuse into heavy elements, so it just sits there and contracts under gravity as more and more helium is added to it. Eventually, that causes what we call shell burning, where the hydrogen outside of the core starts igniting because of the increased gravitational pull from the hydrogen envelope crushing down and that core pulling it in from beneath. And you get this huge increase in the fusion rate that disperses through the sun and causes it to swell up and become a red giant. But that process doesn't just happen randomly. You have to have that helium ash core for that to happen. And the sun does not have that right now. We know because we can tell what's going on in the sun from neutrinos that come to us from the sun and from seismology of seeing how waves propagate through the sun. Even if the sun's core did undergo a sudden and dramatic change and started massively increasing its energy output, it would take thousands and thousands of years at least for the sun to change on a macro level. The inner parts of the sun are very compact, and when energy is generated, it does this thing what we call random walk. It's so dense that the photons come out a little bit, then boom, run into an atom or something like that. And then they turn and move another direction, and boom, run into that. And then change and move another direction, boom. And they have to do these random collisions all the way until they finally get out to what we call the convective zone of the sun, where they can finally get free. The core of the sun is like the most crowded party you've ever been in, and it takes anywhere from 10 to 100,000 years or more for energy to get out. So if you're pumping more energy into the sun, it's going to take a while for that radiative zone and the convective zones of the sun to expand and respond to that. So it's not going to happen. Even if it does happen, this line about how the solar system won't exist in 300 years, we know that planets are orbiting around neutron stars and white dwarfs, the dead husks of stars that have already died. So yes, the inner planets of the solar system might be engulfed, but the outer planets will be just fine. But we know this process doesn't happen randomly because we study lots of stars. What I'm showing on the screen now is a piece of science we call the Hertzsprung-Russell diagram. It is the crown jewel of 20th century astrophysics. It shows how stars behave on a star-to-star level. What you're seeing is brightness of the star plotted against temperature. Brightest stars are towards the top, faintest stars are to the bottom, hotter stars are to the left, cooler stars are to the right. And you'll see they're not just distributed higgly-piggly all over the place. They follow this long diagonal from small, faint, cool stars to large, bright, hot stars. That's what we call the main sequence. That's where hydrogen-burning stars are and where stars spend most of their life. There are those parts that come out of there, those branches, are red giant branches and supergiant branches. Those are stars that are in the process of dying. That will eventually happen to the sun. But this is something that we see, that all the stars are along this line, because a star's properties are mostly determined by its mass. The bigger the star, the faster it burns, the shorter the lifetime, the quicker it leaves that main sequence, it becomes a giant or a supergiant, and eventually ends as a white dwarf or a black hole or whatever. We can see in globular clusters and open clusters groups of stars that have the same age, and they're not just randomly becoming red giants. Below a certain mass, all the stars are main sequence. Above the certain mass, they're all red giants or dead stars. We know that there's a very precise clock that ticks down in every star we see, that when it gets to a certain age at a certain mass, that's when it begins to die. That's when it runs out of core fuel and begins to depart and become a red giant. The sun is nowhere near that, and would be a huge violation of everything we know about physics. I mean, think about it. If a star is going to swell up like that, it has to have lots of energy to do so. Where's the energy coming from? When the sun becomes a red giant, that will come from the shell of burning hydrogen that's fiercely burning and pumping out more energy into the envelope of the star. Where would the energy be coming from to suddenly make the sun swell up like that? Now, in the short story, it's actually worse. The sun is about to go supernova early. The sun is never going to go supernova. It does not have enough mass. Only stars that are at least 8 times the mass of the sun have enough energy to go supernova. A supernova is a tremendous explosion. The energy has to come from somewhere. The place it comes from is gravity. Everything about a star is determined by the gravity. All the energy a star pumps out is eventually gravitational energy. When I was an undergrad, we read an astrophysics book by Frank Hsu, and one of the things he pointed out was that when you look at this, how a star ends, and you look at how it began, all the energy came from gravity. All the nuclear fireworks and stuff in between, in the end, doesn't matter that much because it's eventually all created by gravity. That's the path it takes through burning hydrogen and supernovae and white dwarfs and so forth. But in the end, it's all gravity. The sun does not have enough gravity to become a supernova. There does not have enough energy right now to become a red giant. So this is just kind of garbage. Now, I will detail how they could have avoided this problem. They could have had everything about this plot intact without violating the science. But I'm going to save that for the end of the video.
In order to maximize the chance of human survival, the United Earth government decided to propel Earth out of our solar system to fly toward our new home 4.2 light years away. This mighty and enduring human migration is named the Wandering Earth Project.
The nearest star is indeed Proxima Centauri. It is 4.2 light years away. It is a small red dwarf, so it would be pretty stable, and we could go into orbit around it. The path they show here is wrong. Alpha Centauri, the system of which Proxima Centauri is a part, is about 45 degrees up from the plane of the solar system. All the planets of the solar system sort of move in a disk structure from the disk that they formed out of. And Alpha Centauri is sort of 45 degrees up. So you'd have to go not only out, but sort of up to get there.
We'll devote every possible resource to construct 10,000 Earth engines on the planet's surface to propel Earth out of the solar system.
The height of every propulsion engine is 11,000 meters. They will provide a total of 150 trillion tons of propulsive force.
Here we start getting some numbers. They have 10,000 engines that are going to produce 150 trillion tons of force. That means each one is about 20,000 times as powerful as our most powerful engines that we've developed. But you're 100 years in the future, maybe they've discovered some crazy technology. Now, they later say that this voyage is going to take 2,500 years, and I actually ran the numbers on this. You actually don't need that violent an acceleration. You know, if you have an acceleration about 2.6 times 10 to the negative 8 meters per second, or a tiny fraction of the gravitational force we have every day, over the course of hundreds of years, that's going to push Earth out of the solar system. You don't necessarily need a huge force to cover large distances. If you have a constant force that is acting every hour of every day for years and years and years, you will slowly build up to an enormous speed. One of the projects that NASA talked about for a while was using solar sails. These are giant fabrics that would capture charged particles flowing out of the sun. And that would provide a sort of wind, a solar wind, that would push that spacecraft like the age of sail. The acceleration would be very low. In the first couple of days, you maybe move a centimeter, but it would slowly build up and build up and build up. So after many years, you'd be going very fast. So you don't actually have to have a huge earth-shattering, no pun intended, acceleration to move Earth out, as long as you keep going for a long time. And 150 trillion tons of thrust, I actually figured out, if you run the numbers, that's within the ballpark of what you would need to produce the kind of acceleration they're talking about. So the numbers here are actually kind of accurate, even if the idea is kind of fantastical. There's a video in the description below that goes through some of the calculations of how you would do this. I'm not going to redo those since he does them quite well. Depending on how efficient your engines were and what kind of acceleration you were doing, you might actually have to use up the entire mass of the Earth to accelerate the Earth out. The plot that this movie goes into is different from the short story. The short story focuses on a conflict between people who believe that the sun is going to go supernova and that they have to move the Earth, and people who don't believe it and think that if people want to leave the Earth, they should build giant spaceships and leave the Earth where it is. Count me in the giant spaceships crowd. If you're going to have this whatever technology that could produce such enormous amounts of thrust, why not build spaceships? You know, you could build Broussard ramjets that as they go through space, they suck in hydrogen to fuel their engines. There is so much you could do with spaceships, and it seems like a much more tenable idea than moving the entire Earth. I'm also not clear on what happens to the moon in this scenario. You know, we have the Earth, and we're orbited by this satellite called the moon. What happens when you move the Earth out? Is the moon going to like crash into us? Are you moving the moon away as well? I would have liked to see some addressing of what's going on there. There's an aspect of this, they cover this more later in the movie, but I'll address it now, which is that they stop the Earth from rotating. That they stop the Earth's rotation and build the engines only on one side of the Earth so that it can produce this constant boost to get them out of the solar system. This seems to me, of all the things in this movie, probably the most insane. I'm not sure why you would do that. First of all, as they note, you cause an enormous catastrophe. There are gigantic tsunamis and earthquakes and so forth. That's understating it. The surface of the Earth isn't a solid object. It's plates moving over a molten mantle and gradually shifting over the surface of the Earth. If you attach all the engines to one of these plates, you're just going to slam it into the next plate. And you also then end up with an Earth that has a solid stationary surface and a rotating inner core and mantle. I have no idea what that's going to do. No one does, but it can't be good to have that going on. But in addition, why? First of all, you're stopping the Earth from rotating, all right? So you stop it here. Here's the sun. We'll make the sun the small one. But what happens? The Earth is still rotating. As you push the Earth out, it's not going to just go out like a slingshot. What you're going to do is gradually extend the orbit of the Earth around the sun, making it more and more elliptical. You know, if this is the sun, you're going around it like this in a circle, more or less a circle what Earth is doing. As you accelerate, that circle is going to start getting longer and longer and more elliptical until it finally gets hyperbolic and you're escaping from the solar system. What happens when the Earth rotates around the sun if you stopped it? This is the side where your engines are on, let's say. You move around the sun. Oops, now you're pointed 90 degrees from the sun. 6 months later, you're pointed towards the sun. 6 months later, you're pointed back in the wrong direction. You have to actually synchronize the Earth's rotation with the sun so that as it revolves around the sun, it rotates on its axis once a year so that it has the same side facing it, just like the moon. That's why we always see the same side face of the moon. As the moon revolves around the Earth, it rotates on its axis and keeps the same side facing us. Those are the same period. It's what we call tidally locked. You'd have to artificially tidally lock the Earth's surface to the sun. But it actually gets worse because you're moving further out. That orbit is changing. The speed at which the Earth has to rotate to keep its engines pointed in the wrong direction is constantly changing. So you're constantly going to have to be using these torque engines to change the direction of the Earth. They also have the pointed wrong. They have the engines pointed towards the sun. That's not what you want to do. The Earth already has an enormous velocity around the sun, 30 kilometers a second. You don't want to fight that. You want to use it. You want to accelerate the Earth around the sun so that it's going faster and faster into a faster and faster orbit, so that here's your speed now. You're just adding speed to that to get a more and more elliptical orbit until you can finally escape. What makes way more sense is to build the engines all over the surface of the Earth. And then as they rotate, as the Earth rotates, turn them on and off in cycle. So that they say have 6 hours on when they're facing the direction you need to accelerate, and then 18 hours off so they can cool down, you can do maintenance, you can refuel, you can take dramatic selfies of yourself poised over the Earth engine, whatever. But it makes more sense. Now that does cut the amount of thrust you're generating. But remember, constant boost. You don't have to have this massive acceleration to leave the solar system. As long as it's constant, as long as it keeps going every day, every hour, every day, even if you've cut the acceleration in half or by a quarter, you're still going to eventually get out of there. If it takes 2,500 years to reach the nearest solar system, or 5,000 years to reach the nearest solar system, that's not much of a difference. Your underground cities or whatever are still going to have to be self-sufficient for an indefinite period of time. And so rather than causing this unnatural catastrophe of slowing down the Earth's rotation, just use the rotation to your advantage. That also means if you need to make course adjustments, you just change the timing of the engines around the equator. That also means for the catastrophe that happens later when they're near Jupiter, they could adjust their course on the fly much more easily because you have engines all around the Earth. The Earth is constantly rotating, so you can just change the sequencing of those engines to get the thrust and the power and direction that you want it to. It makes much more sense to just leave the Earth rotating and use the engines that way. This makes no sense to me, and it's probably one of the weakest parts of both the short story and the movie. I will say a lot of the shots of this movie, a lot of the stuff it shows is pretty impressive. So minus 84 C for the temperature, that's really hard to estimate. At this point in the movie, they're out near the orbit of Jupiter, but the atmosphere still exists. It hasn't frozen yet, so you have a lot of carbon dioxide and greenhouse gases still trapping some heat on the surface of the Earth. So you wouldn't have the minus 270 or whatever you get on Europa or somewhere like that. But you also have, they're on the side of the Earth that's constantly facing the sun because they're thrusting in the wrong direction. So you have that heat and that's you're still in the sunlight. So minus 84, you're throwing out a bunch of stuff here, but that seems in the ballpark of what would be reasonable. And is important because it still means the Earth has an atmosphere. The atmosphere has not frozen yet because it hasn't gotten that cold.
There's no other way. Earth can't leave the solar system without using Jupiter's gravity. This is a risk we must take.
So this is interesting. They're using Jupiter's gravity to slingshot Earth out of the solar system. Gravitational slingshots is something we do a lot of in NASA. It's the way we get ships into the outer parts of the solar system and into interstellar space. The idea is that you have a large planet and then a small space probe, and the space probe slingshots around the planet. Now, if the planet weren't moving, that wouldn't get you anything. The amount of energy that you would gain falling towards the planet is equal to the amount you'd lose moving away from it. But the planet is moving. So what happens is you borrow a little bit of that planetary motion, and because the planet is way bigger than your space probe, it gives the space probe a huge acceleration for a tiny, tiny deceleration of the planet. So we do gravitational slingshots of all the planets. This is a very good principle here.
Jupiter's gravitational spike detected. Earth's trajectory is off course by 9.23 degrees. Due to Jupiter's gravitational spike, the probability of colliding with Jupiter increases. Analyzing data collected. Transmitting to the United Earth Government. Disaster warning protocols activated.
A gravitational spike is not a thing that exists. Gravity is one of the most constant forces in the universe. We have been measuring the orbits of the planets for literally thousands of years. We have been measuring the orbits of the moons of Jupiter specifically for centuries. We measure gravity in all kinds of contexts, and you don't get gravitational spikes where gravity suddenly increases for no reason whatsoever. Jupiter is extremely stable. Its gravity is not going to increase or decrease on any kind of dramatic level anytime soon unless some rogue planet comes in and collides with it. This is one of the biggest difference between the short story and the movie. In the short story, the conflict is between those who think the Earth should stay and those who think it should go, and people who don't believe that the sun is going to go supernova and people who do. So it's more of a political fight. In this one, they introduce this idea of a gravitational spike. Jupiter's gravity suddenly increases, and then Earth's going to come crashing down onto the surface. Now, I'll also note that their response to the gravitational spike is entirely wrong. It is intuitive, which is why they do it in the movie, but it's entirely wrong. So here's Jupiter, here's Earth. Earth was going to go around Jupiter like this in a slingshot. Now, because of the gravitational spike, it's going to come down and collide with it. And so everything in the movie from this point on is trying to push Earth away from Jupiter like this, which makes intuitive sense, but is wrong. Remember, we've talked about this many times on this channel, how orbits work. The way an orbit works is you are going around a planet and you're constantly falling towards the planet. Gravity never goes away. But you're moving so fast that by the time you fall towards the planet, you've gone all the way around. So you're constantly falling towards the planet and moving around it so that you have this stable orbit. This is just a different type of orbit. It's a hyperbolic orbit, so you're going around the planet and never coming back rather than a circular orbit, but it's an orbit. You're going around Jupiter. You're going to fall and hit the surface. What do you want to do? You want to accelerate towards Jupiter. You want to go faster and faster and faster so that you skim over it and get around it so that you don't fall to the surface. If you push away like this, as intuitive as it is, you're going to doom yourself because Jupiter is going to keep pulling you down. That velocity you've got is going to keep you going this way. All you're going to do is sort of delay the inevitable. Accelerate towards Jupiter, daredevil it all the way through, and get around. If you can time it just right, you might be able to stay out of the Roche limit, which they'll talk about later, and we'll talk about later, but that's what you want to do. And this is one of those examples where stopping the Earth was a stupid idea. You have this sudden adjustment you have to make. Boy, it'd be really much easier to do if the Earth were still rotating and you could just change the sequencing on your engines to adjust your course that way. It's much harder when your engines are all stuck facing one way, the wrong way, and you can only go in one direction. So you're not going to believe the way they fix this problem, but we're going to get there.
Delta, scout the area.
All right, so what's happened at this point in the movie is they come to the city of Shanghai, and the Shanghai city is buried in ice, like a kilometer deep. Why? Now, they explain this later in the movie that when the Earth's rotation was stopped, still with the stop rotation of the Earth, that caused massive tsunamis and flooding, and a lot of people were killed, half the Earth's population was killed, blah, 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 blah. But those waters would have receded. They wouldn't have just frozen in place. And they especially would not have just frozen in place in like a cube centered on Shanghai. So this is, it's a beautiful, evocative shot, but it makes absolutely no sense. They do have, later on in the movie, something really cool happens that's kind of scientifically accurate. That drone they just launched eventually plunges from the sky because the Earth is losing its atmosphere to Jupiter. This is actually accurate. If the Earth is near Jupiter, the side where Jupiter is doing what? It's exerting a tide on the Earth. What a tidal force is the gravity on the side of the Earth closest to Jupiter is stronger than the gravity of the center, which is stronger than the gravity exerted on the far part of the Earth. And if that difference is stronger than the Earth's gravitational pull, it's going to start pulling things off of the Earth. Now, we're used to that with the moon. That's what causes, the moon's gravity causes tides on the Earth. With Earth, it's frozen, so you don't have that water, but you do have this atmosphere. And so Jupiter starts tidally pulling the Earth's air away from it. Now, it's not going to be as dramatic as what they show in the movie. It's not going to make the beautiful visuals that they show in the movie, but it is semi-realistic, and by this movie's standards, it's extremely realistic that it would do this. And so what you have is kind of cool that they realize this because airplanes and drones start falling out of the sky because they can't generate lift anymore. So that is something kind of cool that the movie does.
The distance to Jupiter is still decreasing.
Of course it's decreasing. Gravity didn't cease to exist. You want to go skimming over the surface.
In 3 hours, the Earth will breach Jupiter's Roche Limit and begin the inevitable disintegration process.
Roche Limit is an actual thing. If you have one body orbiting another, if it gets close enough, it will actually start to tear it apart. Jupiter's tidal gravity, the difference between the gravity on this side of the Earth and this side of the Earth, will be stronger than the gravitational force holding the Earth together. When that happens, the Earth will come apart and disintegrate. I ran the numbers. That happens at a distance of about 56,000 kilometers or about 10,000 kilometers above the atmospheric surface of Jupiter. And so this is actually kind of a realistic depiction of what's going to happen.
In order to sustain human civilization, Moss will initiate the Helios project. 300,000 human embryos are stored on the navigation platform space station, along with 100 million seeds of basic crops, DNA maps of all known animals and planet species, and digital libraries of all human civilizations.
So they fall now to their backup plan, which is to have the navigation station, this massive space station that's been going in front of the Earth to sort of guide it, is now going to leave the Earth, and it has all these embryos and all this DNA and so forth, then it's going to recreate the species. You can't actually recreate animals from DNA. There's more to us than just our DNA. There's mitochondria and RNA and epigenetic factors and stuff like that. This is what they probably should have done in the first place. I mean, it's a good backup plan, I guess, but for the cost of moving the Earth like this, you could have built like 1,000 of these Helios projects and sent them all over the universe and basically ensured that the human race survives somewhere rather than having just one space station that you've now got all your marbles in. So this is another place where I think, just build a spaceship. You know, all these movies seem to like go out of their way to not build spaceships. Spaceships are fun. I love spaceships. So just build a spaceship.
Jupiter is like a huge balloon composed of 90% hydrogen.
If we mix Jupiter's and Earth's atmospheres, is that combustible? By now, Jupiter has siphoned at least 30 billion liters of oxygen. The combustion shock point will be over Mach 1,000. The generated force will be sufficient to push Earth away. The hydrogen-oxygen mixture can be ignited with a single match. All we need now is a match. No. The distance between planets is over 70,000 kilometers. Even ballistic missiles can't reach that far. What about that as a match? What match?
Okay, so their idea here is that Jupiter's been sucking off this oxygen-rich atmosphere from Earth, and now it's mixing with the hydrogen on Jupiter's surface, and so they're going to send this blast of energy to ignite it and create a huge explosion that's going to blast Earth back away from Jupiter. First of all, this wouldn't be enough force. I actually ran the numbers here. If you took the entire atmosphere of Earth, all its oxygen, and ignited it in the presence of Jupiter, you'd produce a blast of about 2 billion megatons. That sounds like a lot, but remember, you have 150 trillion tons of thrust available to you from these Earth engines. What's probably going to happen in this case is Earth is coming in. You're going to send this blast outward, and then it's just going to fall back in. You remember, you need to accelerate along that orbit. You need to increase your speed. And so this isn't going to work. And that blast energy is going to be way too little to do this. So I'm sure some writer thought, hydrogen, oxygen, explosion, Hindenburg. No, you're not going to have a giant Hindenburg explosion that's going to save the Earth. It's just not going to work that way. Sorry. And even if you could produce enough energy, remember, one of the things I said about these engines, the thrust they produce is very gentle. It's 150 trillion tons of thrust, but the Earth is really huge. So the actual acceleration they're producing is very, very, very tiny. Now you're going to produce a huge acceleration that's going to push Earth away, that's going to be much, much more destructive than anything that's been happening so far. So even then, I don't think it's going to work. So again, this is one of the problems they have with the movie with doing this way. The short story focuses way more on political and cultural conflicts and does not have this kind of silliness with Jupiter. And it makes for a very exciting movie. The last half of this movie is very exciting. Again, the comparison to Armageddon, I think, is appropriate because the last half of Armageddon is very exciting if you turn your brain off and don't think about what's happening.
I promise you'll see me. Come on. My son.
Again, the Armageddon comparisons, the father figure sacrifices himself so that the son may live. It's a nice scene, but tears don't float in space like that. It makes for a nice visual, but you can actually see this. Chris Hadfield's done videos on this. When you get tears in your eyes, there's not enough to break the surface tension, so that you just sort of get water around your face. He does this thing where he takes a rag and squeezes it, and you can just see this sort of surface of water around it. It's actually really cool. So it's a nice visual, but scientifically inaccurate. This is a very successful movie. The critics liked it. A lot of audiences loved it. The comparison to Armageddon that I've been making throughout, I think, is very apt. This is a wildly scientifically inaccurate movie. Deals with a lot of really interesting concepts, just like Armageddon did. So it's very slick. It's well made. There's a lot of striking visuals. The last half of the movie has some really great momentum and some moments in it. But in terms of scientific accuracy, whew, Nelly, this is probably what it has to go with among the worst I've seen. So I'm going to say at least 4 face palms, 4.5 face palms. This is not quite 5. I have seen one movie that's a 5, and I'm going to save that for later in the year. But overall, I don't not recommend it. I think that you might find it entertaining if you like science fiction movies. As I said, it's well made, but you're going to have to turn your brain off. So that's it for a while. I'll be back in a few weeks with something else. Oh no, wait. I promised I would tell you how the plot could have been fixed. The plot of this movie, the entire plot of the movie, and 90% of the scientific errors could have been fixed with 3 simple words. 3 of the most beautiful words in the English language. No, not those. No, not those. Rogue black hole. We have come around in a universe that is 14 billion years old and has had generation after generation of stars. And if those stars were big, they left behind black holes. Most of those black holes are invisible to us. Unless a black hole is accreting material from another star or a gas cloud or something like that, we can't see it. It is black. It doesn't give off any light. And so these are just wandering around the galaxy. If one of these black holes were to come near the solar system, doesn't even have to come into it, but come pretty close, it would be the effect on the planets of the solar system would be like 10 pins hit by a bowling ball. A black hole would be a minimum of 3 times the mass of the sun. And when you have 2 massive bodies like that interacting, the effect on smaller bodies is going to be dramatic. Planets will be kicked out to different orbits. Some of them might be injected from the solar system entirely. And so if you had, instead of the sun going supernova, like in this short story, or becoming a red giant 4 billion years early for no readily explained reason, you had a rogue black hole coming in, that would give you the impetus for the entire plot. In that case, the Earth is already going to be thrown out of the solar system. Your response is only to direct it, to change its motion, so that you notice after your calculations, oh, hey, we're going to pass relatively close to Barnard's star. If we build these giant Earth engines and change the trajectory a little bit, we'll drop right into a nice orbit around Barnard's star and be able to survive. That also would have provided the second half of the movie, where instead of a gravity spike, which is not a thing that exists, you could have some unexpected interaction. When you have this many bodies in a chaotic system like that, prediction is hard, and it would be very easy for, say, Saturn to move in an unexpected direction and cause Earth to be plunging into Jupiter rather than skimming around it. And then you'd have to figure out, not the way they do in the movie, but some other way to change it. Maybe you end up playing celestial billiards like Lister and Red Dwarf or something like that. But the rogue black hole solves the problem of why you're moving the Earth. It provides most of the energy you need to move the Earth. It provides the second half where you have some dramatic interaction that you couldn't have expected. And it's a black hole. Black holes are cool. Now, I should say before you start losing any sleep, a rogue black hole hitting the solar system is extremely unlikely. While there are probably millions of black holes in our galaxy, they are outnumbered 10,000, 100,000 to 1 at least by the main sequence stars. And what's more, the black holes, like the stars of the galaxy, are sort of moving with traffic around the center of the galaxy in this nice, steady, circular flow. So they're not just wandering around looking for solar systems to destroy. So it is extremely unlikely. But if you're going to have this dramatic a movie, why not have something that, while extremely unlikely, could actually happen and could provide most of the things and gives you a black hole coming into the solar system rather than this nonsense. I think that would have solved 90% of the movie's scientific problems and still left almost all the story beats, almost all the character moments, almost the entire plot intact. And so I think there was a missed opportunity to make a movie that was not only entertaining, but was relatively scientifically accurate. This would have been maybe a 2 facepalm movie if they'd done the rogue black hole. That's it for a while. I'll be back in a few weeks with something else. Until then, I'm Mike Siegel. I write for Ordinary Times. Thank you for watching.